what is actually the last presentation, which is on extraction strategies, space resource beneficiation, and lithologically complex simulants by Øystein Borgersen at Solsys Mining. And Øystein, the floor is yours. And Tito, can you turn off your screen sharing?
Stop sharing. Yes.
Thank you, guys. Do you hear me okay? I have a new camera set up and everything, so hopefully.
We hear you fine, yes.
All right. Let's see if I can figure out how to share. One moment. We'll just do the entire screen here, and then let's see. Here we go. Okay. Can you see what I see here? Yes. Okay, good. First of all, thank you so much for having us here at LDC2025, and thank you also to the previous presenters. A lot of interesting stuff, and I think actually we will sort of be tangential to a few of them. So I think I'll just jump right into it. My name is Øystein. I'm the CTO and co-founder of Solsys Mining. This is our team, relatively small team for now. Ethel is also on the call, I think. May be available for some questioning later if you want. So we do the most of the work located right outside of Oslo in Norway, and then we also have other people that we pull in when we need it. We are a fairly small startup, in other words. We have something like 10 to 15 years of minerals processing experience from the terrestrial mineral sector. And we also have about 10 years from the startup sector as well, with different things, not just Solsys. All right, so a little bit about also who we collaborate with. Just very short, Norwegian Geotechnical Institute is someone we work with, a little bit with Esrik in Luxembourg, Norwegian Space Agency, ESA, Future Materials. And we also have some people in the US, like Lunar Resources, for example. We have some spacesuit companies and also various ones that we're working on agreements with. So our vision, to sort of be getting to the meat and potatoes here, is extraction strategies. Extraction strategies basically being, how do you build an understanding and a plan for actually extracting something on the moon, which is usable. So basically creating a concentrate to an end user from whatever feedstock is available. And to do this, you need more than two things, but mainly two things that we focus on. Beneficiation systems, that is sort of modular systems that can do various beneficiation tasks, crushing, separation, and so on. And in order for this to be developed and work as close to the lunar equivalent as possible, you also need advanced simulants that are sort of trustworthy in this context. I just wanted to bring up something here that a friend of ours from Tom or Taurus Orbital Mining posted on LinkedIn a little while ago. This is sort of a bird's eye view of what do you call it, like an end use case or a value stream or whatever on the moon, right? So on the left side, you would have extraction, then you would have transportation. In this case, this would be, I believe this is a tubular or a screw conveyor, which goes into a beneficiation unit and then finally ends up with, for example, a 3D printer. And I believe Luis at Tom actually mentioned specifically Space Copy and Solsys, which is really, really cool. So there are people also really thinking about these complete value streams for this, but this is sort of the bird's eye view of what beneficiation is. It basically creates concentrate for an end user, right? So this is where we need to get a little bit into the rabbit hole. I'm probably gonna upset some both lunar geologists and ISRU engineers here with some gross oversimplifications, but I think it's important to keep this in mind. So how do we actually define a rock, right? A rock is defined by the minerals which it's sort of built from, right? In this case, this is troctolite, which is on Earth and also found on the moon. This is sample 76535 from Apollo 17, one of the most sort of famous rocks from the Apollo missions. And a troctolite is defined as being comprised of plagioclase, feldspar, and olivine, right? And these, in turn, these minerals are made from elements. So this is sort of the hierarchy of how rocks are defined, right? But there is also this other side of it, which is the texture or the grain texture. So on the left side here, you can see an ilmenite basalt from Apollo 11. And on the right side, you can see a norite containing ilmenite from Titania or Kronos Titania in Norway, actually. So if any one of you has ever used any sort of European source of ilmenite for ISRU experiments, it's very likely from this site in Norway. I think they extract something like 15 to 20% of the ilmenite on a sort of global basis. So what's important to keep in mind here, or important to observe, is that the textures here are very different. The black stuff, by the way, is ilmenite, and also some other sort of opaque minerals, but mostly ilmenite. And first of all, the right side here is quite a bit more rich in ilmenite than the left side, right? So concentrations of about 35 to 45%. And the lunar one is, depending on it, this, I believe this is like a, well, I should be careful now. This is probably a high TI ilmenite basalt sample, which is about 10% or something ilmenite, I believe. Correct me if I'm wrong. And then the other part of this is how these grains are actually interacting. Are they enclosed by other minerals? Are they sort of touching each other? Are they grown into each other and so on? And all of this is something we need to take into account for the lithic fragments or the rock fragments on the moon if we want to beneficiate them, right? There is also a lot of other fragments that are sort of breccias and agglutinates and that kind of thing. We're not going to touch much on those at all. So the ways they do this on Earth is, in order to extract, for example, this ilmenite that we just looked at, is that you would crush the rock. This is like from an open pit in Norway. So they would crush it, grind it, do a lot of different types of separation, dry and or wet, and you would end up with a concentrate which is dewatered and sort of solid liquid separated. And that's your ilmenite concentrate, right? Okay, now we're going to switch over to a project that we've done, that we completed last year with ESA, just to sort of prove how this will affect your beneficiation or your ISRU experimonics potentially, right? So this project looked at how can you actually extract plant nutrients to create hydroponic nutrient solution for growing plants on in situ, right? We didn't look that much into the plant side or how you would grow it, right? That's for someone else to do. We are only focused on the beneficiation and the extraction strategy behind this. Okay, so what we found was through 45 different extraction strategies, a bunch of samples and a lot of data points for particle size distribution, ICP-MS of all the different elements, as well as ion chromatography, to sort of match this to a hydroponic solution, which is standardized, called the Hoagland solution. We found that you can absolutely extract valuables for this type of application, but it is very likely to be sort of it's not going to have the right amounts of the different types of elements and ions, right? So elements like magnesium, calcium, phosphorus, and so on. But it is possible, right? But to do this, you definitely need beneficiation, right? And then a proper extraction strategy to do this. And this was done, by the way, through both wet and dry methods of beneficiation, as well as combinations of these. So, typical methods would be acid or alkali leaching, grinding, or magnetic separation, that kind of thing. So what we also think we observed, pretty sure that the simulants used will actually have an effect. I mean, it sounds obvious, right? But the type of simulant will definitely have an effect. And this is why, kind of trying to make a joke here about minerals processing and how similar it is to simulant production, because it is, at least for most of the simulants that are used these days, right? So again, rocks are defined by the minerals that they sort of are made from, right? Whilst simulants nowadays are often made with already liberated concentrates, right? In addition to raw rocks, of course. So I'm not going to tell you which supplier this is, but let's call it a random simulant like this. You can see here in the text box. include something like almost 50% concentrates, right? And this will definitely have an effect on how easy is it, for example, to pull out ilmenite if the ilmenite is already liberated in the simulant itself. This is very different from ilmenite actually being stuck in a matrix of basalt or glass or pyroxene, that kind of thing, okay? So what we started doing after this project with ESA is that we started developing a simulant which is based on no concentrates at all. It is only based on raw rocks, right? So the one on the right side here is typically norite and anorthosite troctolite. And the left one here represents sort of a more traditional simulant, which is made typically from maybe one raw rock as well as mostly concentrate, or at least a large part of concentrates, right? And these have been through potentially wet beneficiation steps, and they are relatively pure, right? So they're already separated from these lithic clasts that you usually find minerals in on the moon. There is already liberated stuff on the moon for sure, because it's all been comminuted and ground up by impactors, right? All right, so in order to put this to the test, this simulant, right, we got another contract with ESA, and in this one, instead of doing a sort of a shotgun on a target, doing a lot of different extraction strategies, here we are aiming for a sort of, or a very, very tight, like a sniper rifle set of extraction strategies instead. And we're gonna compare the simulant that we are making ourselves, called Lunar, with these different types of already commercially available simulants. And then we'll see, will there actually be a difference in extraction efficiency here? Like, is it easier to get stuff out of a concentrate-based simulant than a raw rock-based simulant? Very likely it is, but we'll see. So this project is about extraction strategies aiming at pulling out specific elements that can be combined with source-separated urine from the environmental control and life support system to create a hydroponic fertilizer that way. And we're doing this. This is again supported and funded by ESA, and we're doing this together with the CERES, which is the Center for Interdisciplinary Research in Space, located in Trondheim in Norway. All right, just to show you a little bit about how these different rocks sort of fit together, how they're built from minerals. Some of you have probably heard about anorthosite, right? Maybe some norite and troctolite as well. And these minerals also fit together with basalt. It's basically okay, I need to be careful now. It's basically many of the same minerals in different, or same mineral groups in different ratios and different textures. But again, they are fairly similar. So we think it is a very good idea to start, instead of focusing just on particle size distribution, for example. Of course, this is important: particle size distribution, particle shape or morphology, and chemical or elemental and mineralogical fidelity. We think there is also a really good case to be made, specifically or especially for beneficiation and for other things like dust mitigation, where you're getting into electrostatics, that lithologically complex simulants, that is, simulants that have minerals in these clasts and rock chips and is made from actually rocks containing these minerals. I think there's a pretty good case to be made for creating those, and that they have a really quite high value in this segment that we're working in ISRU. So in short, for ISRU, we think extraction strategies are they're absolutely critical to have a plan between your raw material and your end user. In this extraction strategy, you need beneficiation. You need different types of modules to do the different types of processing. In order to develop these, you need lithic simulants that really simulate these more complex particles, right? And our sort of answer to this that we're testing out these days is called Lunar, which is a series of both Highlands and Mare simulants. And again, these would also work for other applications like dust mitigation, for example. So I think that's about it. I don't know how long time I used, but I felt like I just rushed through that. So yeah, if there is any interest in having a chat with us, again, we're laser focused on beneficiation and extraction strategies. If any of you want to have a work with us, we would be very happy to have a chat for sure. All right, thank you.
Thank you, Øystein. Any questions on that? Yeah, Frank?
Yeah, is Colin Lennox in the participating members? I think he's, if not him, like definitely Pat Groves is going to want to look into this because he's also been looking at these types of strategies for beneficiation.
So just to be clear about this, we really like to see numbers like 1,000 tons per hour, like Mark presented earlier. We're looking into this sort of industrial direction here. We want to do, not necessarily science experiments, although that is a very important part of this as well. Don't get me wrong, but we're looking at the industrialization side of this, right? Which we think is really, really interesting.
That's good. Stuart?
I have two questions. First one is, like, when you go to a new mining site, like just on Earth, how much tweaking do they have to do to the beneficiation process to get the right concentrations? Is that it takes days, weeks?
Yes. So typically you would do a bunch of different what do you call it? A bunch of different campaigns, basically liberation analysis, like how easy is it to how far down do you need to grind this to actually get economic liberation of your minerals, right? And then, of course, it depends so much on what you actually want to get out of this. Like, is it a platinum concentrate that is your end target, or is it just like an olivine concentrate for the foundry industry or something like that? It all depends, but yes, there is a lot of work involved in it, and not just about the comminution, crushing, grinding, and liberation. There's also this whole process afterwards. Can you do it cheaply and sort of with less complexity dry, or do you actually need to pull in hydrometallurgical methods with all this entails with tailings and backfill and pasting and all this stuff? So it is quite an involved process indeed.
My second question is electrostatic mineral separation still a thing? Is it still used? Is it still a direction?
Absolutely, yes. So I'm glad you asked, because I don't know if you've noticed this in one of my earlier slides, but there is this sort of particle texture or grain texture called poikilytic, right? Which basically means that grains are completely enveloped by other grains. So electrostatic potentials, or the electrostatic sorting, basically is based on how much charge can the surface of the particle retain, right? And this is based on the mineral. So if you have one mineral enclosed by another, electrostatics will sort on what is on the surface and not necessarily what the particle is mostly made of. So this is also a very good case for lithologically complex simulants, because they pull in these classes of complex sort of mineral assemblages instead of already liberated ones again. So I think the main point here is that I'm afraid that a lot of the studies done so far, for example, of magnetic and electrostatic separation, I think they're overestimating the yield or the efficiency at which they're extracting at this point. But yeah, thank you for the question. Really, really cool.
Oh, I'm going to squeeze in one more question. So if you over grind in your beneficiation, is that a problem?
Yes, it is. So one example on that we actually did in our ELISA study, the first one with the plants. So if you want to do magnetic separation, right? Maybe we thought, okay, there's a bit too much iron in the leachate that we're getting out for the plants, for the fertilizer. So let's try to magnetically pull out the iron, right? To lower that, and sure, it works. So we're like, okay, but we're pulling out other stuff at the same time that we're pulling out this bad iron. Like some other things are sort of sticking, right? So okay, let's grind it further down so that we know that we have better liberation, so we can pull out more of just the iron bits, or just the iron bits, But what happens is when you grind finer and finer, the forces in between the particles, the adhesive forces and so on, they actually overpower the effect from the magnetic separation unit. So your magnetic separation efficiency drops with particle size. basically. So there are some ways to mitigate this, but yes, it absolutely affects it. And there are sweet spots for all of these, or particle size sweet spots for all of these different types of separation methods.
So you have to separate in the right order.
Yep. Yes. So order matters a lot. So in our case, again, we tried magnetic separation first, grinding afterwards, and then grinding first, magnetic separation afterwards. And those two have very, very different results when you look at the ICP or leach numbers afterward.
Cool.
So do I have a little bit more time? Can I ask one more question? So the lunar dust, is the lunar dust too finely ground already?
It depends. It depends. Like, again, it depends so much on what kind of liberation you're looking for, right? And so I believe the Maria is typically around 50 to 60 micron D50, or like the medium particle size. And that is absolutely not too low to do separation, but you will see a drop off in efficiency on the lower sizes for sure. In the highlands, though, I think it's a different story. There, you would potentially be able to liberate more particles with increase, or with sort of assisted comminution or particle size reduction to get a better liberation efficiency. There's also this other case to be made that maybe there's been some sort of preferential comminution happening on the moon, so that in the smaller sizes you would maybe find more of one element or mineral than the other sizes, right? So you might be able to beneficiate not just by size, but also by element and mineral, just by sieving it, right? But yes, it is harder in some places on the moon, but it's not over grinded. No, I wouldn't say that.
Great, thanks.
Very interesting. Yeah, and I think that concludes the presentation bit.